back. So the last part of the presentation is about the LTE model that we actually developed within the LENA project. Let's start from the high-level requirements of this LTE model. And the aim of this model was to support the evaluation of primary radio level performance and end-to-end quality of experience. And this evaluation was meant to be done for particular kind of algorithms which are expected to be implemented in the simulator. And these algorithms are, for example, schedulers that are quality of service aware, radio resource management algorithms, inter-cell interference coordination algorithms, and in general, as I mentioned before, any type of algorithm that you could think fit in the category of self-organized networks. And finally, one last type of algorithms that probably I didn't mention before is that of cognitive radio dynamic spectrum access solutions. That is solutions that try to use the spectrum in an intelligent fashion, maybe dynamically choosing the frequency and bandwidth in which one base station should transmit, for example. Or maybe opportunistically using some spectrum band that is in an unlicensed fashion or a secondary user fashion. From the point of view of the scalability requirements for the LENA project, the aim was to support from several tens to a few hundreds of base stations and say one order of magnitude more of UEs. So we do not aim at simulating networks with tens of thousands of node Bs. That's a too large network. So, but still, we want to have a scenario, for example, where there are so many node Bs that you create an interesting interference scenario. Typical case is that of having several macros and the area covered by several macros, and then lots of femtocell deployed inside buildings, for example. And well, the design approach that we had for the LENA project is, I would call it an approach that is typical of lots of simulation models. Since simulation is fundamentally a trade-off, in having a very detailed model that mimics a real system very closely, and the complexity of doing that. So you can have more detail, but it is more costly in terms of implementation, and not only implementation, but also runtime execution of the simulation. And the obvious choice, which is normally done, and also the choice which we adopted, is to basically choose the minimum level of detail that satisfies our requirements. And this minimizes the complexity of the implementation and also minimizes the difficulty in using the simulator. The reason is that when you have a too complex system to configure, even as a user, you have to take care of too many parameters to set up, and maybe when you run simulation, if the system is more complex than you need, you end up wasting a lot of time in finding a good configuration. And so here are the most important design choices that we did for the LENA project. This list is by no means exhaustive. There are actually a lot of design choices that we did, and you can find almost all of them in the LENA project documentation. But here are the most important ones. I already mentioned this choice of building the LTE model around the LTE max scheduler interface defined by the femtoforum. Then other choices that are important that we did is, well, first of all, that at the radio level we model wireless signals with the granularity of a resource block. So we do not go to the symbol level. And the reason we don't do it is it's too complex to do so. It will require a lot of implementation, to require implementation of the whole signal processing, and then simulation will take forever. And because of this, we have a simplified physical layer model that, and the channel is, of course, the channel model is designed to work with this physical layer model. For the upper layers, we try to have a more detailed protocol stack. In particular, the one design choice that we made is to have a realistic implementation of the following protocols. So the RRC protocol, PDCP protocol, and then the S1U and X2U protocols. So these protocols all belong to the data plane. And I would say that the most important design choices was that around the RRC protocol. And the reason for having this a realistic implementation, that I mean an implementation that is basically following 3GPP specs, like having all the PDUs with all the features like segmentation, concatenation, reassembly, and so on. This was needed because of the requirement to have end-to-end quality of experience evaluation. So if you want end-to-end evaluation, you need to support a realistic application with IP packets. But LTE does not work with IP packets because at the radio level, performance is determined like by transport blocks that are transmitted and so on. So in order to map properly an IP packet to a transport block, you need to have a realistic RRC implementation that takes care of the fragmentation of an IP packet. So that's the reason why we have an almost complete implementation of RRC inside our model. And then for the other model, we chose to have them accurate models because, again, of the same requirement of having an appropriate end-to-end quality of experience evaluation. So we can say that basically all the end-to-end path from the UE to whatever remote host on the internet is modeled in a rather accurately fashion. There is one exception which I will mention later. For the control plane, well, we actually choose a hybrid approach. We have simplified model for some interfaces, in particular the control part of the S1 and the X2 interface. And also for the S11 interface, we have a simplified model. This means, for example, that we do not implement the whole specification. We just have, we select a subset of the primitives that we need for the simulation to work properly. And we implement this primitive in a simplified fashion. Sometimes it may be, with some actual packet that looks like the real packet in the 3GPP specs, but maybe does not comply with the encoding, like with the ASN1 encoding, which is very complex to work with. Or some other case, for example, for the S11 interface, we just use, direct function call between modules to pass the information without having actual messages. For the EPC part, well, we have one important assumption is that we are working with a single MME and a single SGW. And the other important assumption that we have is that the SGW and the PGW are in the same node. This is consistent with the fact that, well, there is a limit in the type of network we are going to simulate. So we think it's reasonable that all the node Bs in this network are served by the same SGW. And by collapsing the SGW and the PGW in the same node, we basically save the implementation, or we don't have to model the S5 or the S8 interface. And another important assumption of the model developed in the LENA project is that it is focused on connected mode. So we wanted to evaluate the performance of flows that are active. And for this reason, we focused on these tuple of states, so RRC connected state, EMM registered, and DCM connected. We actually have, as a future development, we are thinking of modeling some aspect of idle mode, for example, idle mode cell selection. But in any case, we don't have, at least for the short-term future, we do not plan to support like full idle mode mobility and so on. And here is an overview of the system that we are modeling in the LENA project. And this is basically what I said before. So we have the one node that implements both the SGW and PGW. We can have several node Bs. In this picture you see only two, but they can be more. And then we have the X2 interface between node Bs, and the S1 interface between each node B and the SGW, S1 UE interface, sorry, and the S1 AP between the node B and the MME. And as I said, the S1 AP, so the control part basically of S1, is a kind of abstract model or a logical model with no real messages implemented, whereas the S1U, you have the real GTPU protocol implemented. And the blue part in this figure is referred to as the EPC model, and the red part here is referred to as the LTE model. And I think actually it's maybe clearer in this picture, where we see, in this picture, we see only the data plane, but we see all the protocols that are involved. And again, we can see the LTE model here in red, and the EPC, well, the S1U protocol stack here. And as I said, we have implementation of PDCP and RRC protocol, then on top of MAC and PHY, which are a bit simplified, except for the scheduler, of course. And on the S1U side, we have GTPU over UDP and IP. And what I mentioned before is that we designed the simulator in order to evaluate end-to-end quality of experience. And as you can see here, this is achieved by having end-to-end traffic between application, where one node is so one endpoint of the traffic is a UE in the LTE network, and then the other endpoint of the traffic is a node in an application installed in a node in the internet in general. And actually, thanks to ns-3, we can, in the figure here, you see that we just mentioned that there is the internet with some remote hosts, but ns-3 allows you to have lots of different topologies for what is the internet. You can just have one remote host and put all your applications there. It's simple to do. Or you can have a very, very complex network topology to simulate different things. And well, type of application that you can have is absolutely custom. Any application that is in ns-3, you can run it, and so it means you can use both TCP and UDP, and they will work all with the LTE model. And it's not shown here, but it's actually also possible to have communication between LTE UEs. In that case, what happens is that communication will reach the SGW and then go back to the other UE. So this is supported as well. Now, for the rest of the presentation, I will deal with the specific parts of the LTE model, and the approach will be bottom-up, like going from the lower layers, from the channel to physical layer, up to LTE protocol stack, and then to core network and so on. So, from the point of view of channel modeling, the radio propagation models that are used inside the LTE model, well, they have been developed, most of them have been developed inside the LENA project, but they are actually not specific for LTE, and so they have been contributed to the ns-3 project, and actually you can use it even with other wireless technologies such as Wi-Fi, for instance. And these models are mentioned here, like we have a couple of models defined by ITU-R, together with the well-known Okumura-Hata model, which are used for path loss in different conditions. And plus, we have one additional model, which is the so-called buildings model, which allows you to simulate basically the propagation, the penetration loss when you have a communication which is passing through a wall. And in particular, these models distinguish between external walls of a building and internal walls of a building, and allows you to specify different loss coefficients for these types of walls. And then we have a fading model that we also implemented as part of the LENA project, which is a trace-based fading model. So it allows you to specify a fading trace both in frequency and time. And the two examples of fading traces are shown here. As you can see in the figure, we have on one axis we have the resource block index. As I said, the model has a resolution of the resource block, so we have one fading value per resource block. And on the other axis, we can see the time in milliseconds, because we use 1 TTI resolution for LTE. And well, we normally generate traces using MATLAB. In principle, it's a text file, so it can be generated with any other tool that could be available. And by default, with the simulator, we ship a set of traces that cover some common use cases, such as pedestrian, vehicular, and with different multi-tap profiles and so on. And some is more frequency selective, like this is more frequency selective, and so on. They are different characteristics. Finally, we have an antenna model that this has also been implemented as part of the LENA project. It was not available in ns-3 before. And the framework that we developed is general and allows you to model in principle any possible antenna radiation pattern, but the only models that we actually implemented on top of this framework are, well, there is a simple trivial, let's say, isotropic model, and then there are two sectorial antenna models. One is based on the cosine shape and the other is based on the parabolic shape. And these are normally used for sectors of macrocells. Physical layer model, well, one big assumption is that the model is for FDD only. We do not currently support TDD. In the frequency domain, the granularity of the model, like the representation of a signal, it has the granularity of the resource block, and in the time domain we have the TTI. And furtherly, in the time domain we divide one TTI into two parts. The two parts are actually different for downlink and uplink. For downlink, the first part is control, which is 3 symbols, and the second part is data. And on the other hand, for uplink, the first part is control and takes up most of the TTI. Sorry, not control, is both control and data, and takes up most of the TTI. And the last part is just one symbol and is used for modeling the SRS, sounding reference signal, right? The physical layer model uses a Gaussian interference model to calculate interference between different base stations, or UEs in the uplink. And it also provides means for evaluating signal to noise ratio and generating CQI feedback. And since the model is an abstract model and does not implement the whole signal processing, we use an error model in order to evaluate the correctness or not of the transmissions. And there is a slide on the error model later. And so the physical layer interacts with the propagation model, and in particular the assumption for this interaction is that the propagation model is for SISO only. So there is just one value regardless of how many antennas ports are used for the communication. And still the physical layer model includes a model for MIMO communications, and the way this is modeled is by basically considering the SINR gain with respect to SISO that occurs for different transmission modes. This is a simplified model. We are aware of other simulators that did something more complex, like having the complex gain for every antenna pair and then calculating, the actual SINR after recombination. But doing so implies a lot of additional runtime complexity, and that's why we decided not to do it. Besides, even if you had these separate gains for complex gain for different antenna pairs, you would still have needed to do some assumption, for example, on the correlation of antennas in order to have fading traces, for example. So in our opinion, it was like having a very complex model but not really being able to get something more realistic out of it. So that's why we chose just to have the gain. And you can actually tune the different gains that are used for different transmission modes, and in principle this should be done taking into account the correlation among antennas in the scenario that you are considering. And finally, the physical layer model supports a setting of different frequencies and different bandwidths for each E0 B. And you can have, in the same simulation, different E0 Bs with different settings. And these settings can also be such that the base station are using partially overlapped frequencies. And this is done leveraging on another model that is called the spectrum model. It's available from ns-3, and this model was also developed inside CTTC, but not as part of the LENA project, as part of another project. About the error model, so we have several error models. The most important one is the one that is used for data transmission, so the PDCH and PUSCH. And it's a transport block error model. It means that for every transport block that is transmitting in the simulation, we evaluate whether the transport block is received correctly or not. And But still, as I said, the physical layer model has an SINR value for every resource block. So how do we combine these two things? This is done using a technique which is well known in the literature, and it's called the link to system mapping. In particular, we choose one variation of this technique, which is the mutual information effective SINR mapping, which allows to translate basically these vectorial SINR, one value for every resource blocks, into at the end of everything into an error probability for the whole transport block, taking into account the modulation and encoding scheme that was used for the communication, and also the transport block length. And from a practical point of view, this model has been done by taking an existing open source link level simulator. It was a simulator implemented in MATLAB that implements all the signal processing of LTE, and we ran a lot of these simulations, and we got some error curves, so block error rate curves, that are then implemented into our ns-3 LTE model to evaluate the correctness or not of one transport block. And well, all the curves that are implemented are shown here, and there is one curve for every modulation encoding scheme. Well, sorry, one set of curves for every modulation encoding scheme, and for each specific MCS we have different curves for different transport block sizes. So of course, whenever a transport block is transmitted, we approximate the transport block size to choose one curve. So there is a bit of approximation in doing that. But overall, this is much, much faster than implementing the whole signal processing in the simulator. And for this reason, this technique has been, it's widely adopted in lots of simulators. Thanks to the use of the mutual information effective SINR mapping in the error model, we are also able to model, to have a model for hybrid ARQ. And basically, it's due to the fact that if we determine the error probability based on the mutual information of one transmission, we can also combine subsequent transmission attempts in order to determine the overall success probability of the sequence of retransmissions. So this is the error model that we use for HARQ. And additionally, on top of that, we also implement all the management of hybrid ARQ, that is the transmission of feedback, both in uplink and downlink, and the actual schedule of retransmission. The schedule of retransmission is done by the scheduler, and using some primitives that come from that are defined in the femtoform API. So we just leverage that primitives, and these are used to schedule hybrid ARQ retransmission. From the point of view of the MAC, well, we make one assumption about the resource allocation model that is used, that we stick just to allocation type 0. So this is, in the future we might, get over this assumption, but for the moment we are using that. It means also that all our schedulers have to work with this allocation type. And this allocation type is uses resource blocks grouped into resource block groups together with the localized mapping approach. We also provide two different algorithms for adaptive modulation encoding, which are currently used by all the scheduler implementation that are provided within the simulator, even though in principle one could of course implement a customized adaptive modulation encoding algorithms. And one of these algorithms works on like an analytical model that is based on a target bit error rate, but since it's just based on an analytical formula, it turns out not to be very accurate. In particular, it's very, very conservative. And then there is another model that we actually implemented based on the block error rate curves that you have seen for the error model. And this AMC model selects the MCS that the highest MCS that has a block error rate below 10%. This is consistent with 3GPP specs. And in principle, the simulator model supports a dynamic selection of the transmission mode, like you can change from transmit diversity to spatial multiplexing. What does this mean that is supported? It means that, again, leveraging on the femtoform API, you can issue a command, the scheduler can issue a command to change the transmission mode, and the rest of the simulator model will react properly to this command and switch the mode, but no current implementation of scheduler is using this one. So this is left like for a vendor, for example, to implement a custom smart algorithm that dynamically adapts the transmission mode. For the transport block model, well, we have a kind of abstract model, so we mimic a bit the structure of 3GPP in the sense that for us a transport block is a collection of RLC PDUs that are multiplexed into a MAC PDU, but we do not implement the details of this MAC PDU. Particularly, we do not model MAC headers, and yes, we do model MAC control elements, but without actual the data structure as defined by 3GPP. So we just have our own custom structure, and we do not model like the overhead that is caused by these MAC headers. And this is actually consistent with our requirements that we care mainly about, developing and testing schedulers, because normally the scheduler neglects actually the MAC overhead. Well, at least for MAC headers, not actually for control elements, but in fact we have a way of having the scheduler take care of the allocation of resources for control elements. But the MAC headers normally are accommodated by rate matching, which we do not model. So it's something like a lower layer, and the scheduler does not need to worry about it. So that's why we neglected it. And with the simulator, we ship several scheduler algorithms. Actually, only a couple of them have been developed as part of the LENA project, which are the round robin and proportional fair. So one thing that I would like to mention is that even though the algorithms themselves are very simple, if you look like in the scientific literature for the definition of round robin and proportional fair is nearly maybe a few lines of pseudocode. But if you look at actually the implementation, it's several thousands. And the reason is that in addition to the algorithm itself, we also have to support the femtoform API, and every action that is taken needs to be done according to the femtoform API. Plus, there are lots of management issues that actually go beyond the actual definition of proportional fair. Like, as I said, handling, the scheduling of HARQ, handling the allocation of resources for the random access procedure, and so on. And in addition, there are other scheduler implementations which are included in the official version of ns-3 and that were developed as part of the Google Summer of Code in 2012, so last summer. And this is a project that was done by a student, and this was actually supervised by us at CTTC. So yes, we are not the developers, but still in any case we supervised all the work. And all these implementations are done on top of the femtoform API. And well, it is to be mentioned that these algorithms that are on the list are for downlink only. And for uplink, actually all these implementations shared the same round robin algorithm. The reason is, well, this is also due to, well, for the first two algorithms, is due to our initial definition of requirements, that there was more interest in the downlink than in uplink, and also for the Google Summer of Code, where it was, the definition of the work to be done was done together with the student, and his research interests were more in the downlink than in the uplink. That's the reason. Well, another reason, to be fair, is that in the uplink, the scheduler is split between the base station and the UE. So the base station only decides the resources to allocate among different UEs, but then it is the UE that actually implements the allocation of resources to different bearers. So the scheduler in uplink is a bit simpler and maybe less interesting for like proprietary, for like inventing a smart solution and making a patent on it. We have a MAC random access model, which is a bit simplified, The simplification are mostly for the preamble transmission. In particular, we have a kind of ideal model of preamble. So whenever a preamble is sent, it's always received correctly unless it collides in the same cell with another preamble with the same identifier. So the collision model is basically corresponded to what is known in the literature as protocol interference model. So it's like collisions are only logical and not due to SINR. And additionally, we don't have a capture effect, so it means that even though one preamble might have a much stronger power, we pretend that this is never received. If it collides, we pretend it's never received correctly. For the random access response, we again model it with an ideal message that is not subject to errors, but since we trigger the necessary primitives with the scheduler, the necessary fail-to-form API primitives, so that the scheduler can take care of the allocation of resources for the random access response. The same holds for message 3 for the point of view of the scheduler, so it also the scheduler takes care of allocating resources for message 3. But from the point of view of the transmission, it is different in that message 3 is modeled accurately. So we have a real PDU with actual bytes, which is subject to the data error model that I explained before. And we support both contention-based and non-contention-based access for this random access model. The RRC model, as I said, is pretty much accurate in the sense that we have our own implementation of the protocol, which models a lot of the features that you actually find in 3GPP specs, and the features in detail are mentioned here. Like we support segmentation, fragmentation, reassembly, discard of SDUs, and for the particular case of RRC AM, we support status PDUs and retransmission. I mean, this is everything as per the 3GPP specs. There are some simplification, like currently we do not support the resegmentation for PDUs being retransmitted, because when we were developing this we had to introduce some simplification, but actually we are probably going to add this feature because we feel that in some scenarios otherwise the simulation would not behave correctly. And in addition to the model specified by 3GPP specs, we have another model which is called the RRC SM, which stands for saturation mode. It's a highly simplified model with basically it's a model with a traffic generator embedded inside the RRC, so that you can run a simulation with no higher layers and with just one traffic generation inside the RRC, that whenever the scheduler allocates a transmission opportunity will generate some bytes and pretend that this is a data packet. And this can be used to have a simplified simulation setup. For the PDCP model, well, we have realistic headers with the same structures as the 3GPP headers, but we do not support a lot of features. The only features that we support is transfer of data and maintenance of sequence numbers and transfer of SN status for handover purposes. But we do not support header compression, we do not support ciphering, integrity protection, and so on, because they are just not, I mean, we are not interested in evaluating these aspects of communications. Well, actually, header compression would be interesting in the sense that it's important to have, proper end-to-end quality of experience measurements. It's important to take into account header compression. But so far we didn't implement it because of time constraints. And even if at some point we need to simulate a scenario, we probably would play some trick like shrinking the size of a array hazard with some tricks in order to avoid having to implement a complete implementation of header compression, which would be very complex. The RRC model takes care of some specific features. First is the generation and reception of system information, and then some specific procedures specified by 3GPP, which is in particular connection establishment and connection reconfiguration. The latter involves supports only a few specific items. That is, the setup of data radio barriers, the reconfiguration of the SRS configuration index, the switch of the transmission mode for using MIMO, and of course handover. And the model itself is divided into several parts. First part is the logic, which on the UE side. Another part is the logic at the eNodeB side, which is split in two. There is one generic part, and then there is another part which is like the state machine that is inside the eNodeB, but that takes care of a given UE. This is called the UE manager. And plus we have two different models for the transmission of RRC messages, or alternative for the implementation of RRC primitives. One is the ideal RRC model, which is basically just implemented via direct function calls between the eNodeB and the UE, so that no actual RRC packet is transmitted over the air. This is to have like an abstract model that can be a reference performance for an ideal case. Then we have an actual implementation of RRC PDUs as per the 3GPP specs with actual ASN1 encoding. Well, to be fair, we don't have all the information elements that are specified by 3GPP, but we just implement the resource elements, the information elements that are needed for simulation purposes. That means all the ones that are implied for these actions. But once this is said, yes, for the rest, these are implemented following the ASN1 encoding. And according to this real RRC model, the actually encoded RRC PDUs are transmitted over a signaling radio bearer, and therefore this means that the scheduler takes care of allocating the radio resources for these RRC messages. In this figure you can see the UE state machine, so the state machine of the RRC at the UE. And as you can see, there are actually some states for idle mode, but they are kind of transient states that are only used at the beginning of the simulation. And the reason is, what I said in some previous slides, is that the focus of the simulation model is in connected mode. So basically, once the UE goes connected, it stays in connected mode and maybe hands over to another cell, but still stays in connected mode. And we are thinking in the near future to also implement some form of idle mode so that you can actually terminate the connection and go back to this state here where you might perform cell reselection. But currently this is not supported. And the eNodeB state machine, the main difference is that while one UE is, exists for the whole simulation, in the eNodeB, the context of a UE is only created when the UE performs connection establishment or does a handover to that cell, and then can be destroyed, for example, when the UE leaves. And for the decision, you have actually different initial states depending on the reason why the context was created in the eNodeB. Then we have different states for this case, like we check that it has several states for the connection procedure and different states for the handover procedure. And while we are in the connected normally state, we can perform cell connection reconfiguration. And then we can go away from that state when we do handover. In the future, what we'll add is the possibility that you also remove the context if the UE gets disconnected. We have a simplified model for the non-access stratum, and the idea is to model the active state, which is defined as EMM registered and ECM connected, and model this in a simplified fashion. So from a practical point of view, we just implement interaction between the NAS and the MME in a logical fashion with direct function calls, no real NAS PDUs going to the network and back. And the functionality that our model implements is basically the initial attachment, so when you start the simulation and tell one UE to get connected, and the activation of EPS bearer. The other important feature that is implemented is the multiplexing of data, so IP packets, onto different radio bearers. And this is done using traffic flow templates. So you can set up specified templates when you specify the simulation topology. And of course you can configure different applications to use different UDP and TCP ports. And these, together with the IP addresses that you assign in the simulation, can allow you to differentiate traffic on different bearers. And some remarkable features that we do not support is well, the selection of the network or the closed subscribed group, and also all the features that are normally used in either mode. Okay. For the S1, well, we have different level of details. The S1 U part, the user data plane part, is I would say pretty much realistic. So we have an actual implementation of GTPU running over UDP and IPv4, and so that we have actual packets going over a simulated link, and we are actually using point-to-point links to connect the node-B with the SGW. For the control part, it's an abstract interface without any PDO, and we support the primitives that are listed in this slide. For the X2 part, again, we have different level of details. The X2U part is basically implemented in a similar way to the S1U part. So we have an actual GDPU implementation over UDP and IPv4 with point-to-point links also in this case. It's a different link because it's we have one link between every pair of node Bs. Well, actually, you can decide whether you have an X2 link or not, of course. And for the control part, well, in this case, we do have PDUs that implement the primitives as per the 3GPP specs, but the most important difference is that, well, there are two differences. One is that the encoding does not follow 3GPP specs. It's a kind of simplified encoding that we chose in order to have a simpler implementation. And the second, we are not using SCTP as the transport protocol for the X2 application part, but rather we are just using TCP. And the reason is that SCTP is not currently supported in ns-3. And primitives that are supported for the X2, the control part of X2, are divided into two categories. On one hand, we have the handover primitives, so the ones that are used for X2-based handover. And on the other hand, we have so-called SON primitives, so primitives that are used for the implementation of self-organized network solutions, like inter-cell interference coordination. And in this category, we support two specific primitives. One is load information, and the other is resource status update. For the S11 interface, we use a purely abstract model with no GTPC PDU exchange. Again, we just have direct function calls between the MME object and the SGW, and the primitives that are supported are listed here. And well, you can see that there is a mapping between the primitives used here and the primitives used here. And basically, we use this for the activation of bearers at the beginning. Well, not at the beginning, even at runtime during the simulation. Configuration of an LTE simulation is done using the ns-3 attribute system, and which means that there are several ways that you can use to configure to do this configuration. You can do that via an input configuration file. You can do that via the command line. There is a syntax in ns-3 that allows you to specify attributes, or if you prefer, you can put the value in your simulation program and configure it there. And all these methods that I explained are used for changing the default value of some object. If instead you want to change the value but only for a specific instance of an object, then you have to do it either within the simulation program, sorry, there is a typo there, or, for example, using the GTK config store, which is the graphical application that I showed you earlier. From simulation output, we have different KPIs that are available at different levels. Like going over the list from a bottom-up approach, we have channel KPIs in the form of SINR maps. Somebody calls it radio environment maps. And we can also output from the simulation path loss matrices. We have some KPIs at the physical layer. One form is a trace that is used for the transmission and reception of every transport block. Tells you like whether it was correctly received or not, how many bytes, what modulation coding scheme was used, the redundancy version that allows you to get statistics for HARQ transmission and so on. And the other type of traces that we have is the traces for RSRP and RSRQ values. For MAC KPIs, we basically have traces for uplink and downlink scheduling decision. And the tracing format is basically, a summary of all the parameters that go through the Femtoform API. Well, not all of them, but the most important one, and that gives you a quick overview of what was the scheduling decision. From the point of view of RRC and PDCP, for both we have support for generating time average transmission and reception statistics. So you have one file, actually 4 files total, two for RRC and 2 for PDCP, and 2 for downlink and 2 for uplink. And these statistics are like for all the PDUs transmitted in a given window. You count how many PDUs, total amount of bytes transmitted, average delay, standard deviation of delay, and so on. Finally, higher layer statistics such as IP layer statistics or application level statistics can be obtained with all the available ns-3 methods. And well, a very popular method is to use the flow monitor, which is a framework that gets you a lot of stats for IP flows. Or you could use pickup traces generated at the UE or generated at the remote host in the internet. Or you could directly query the application for getting the stats, such as how many bytes have been received and so on. Here is an example. Fortunately, I'm not sure you can see it very well from the projector, but of the, I would call it the most important example program that we ship with the simulator. It's called the dual stripe scenario. And so this scenario is a scenario with some macro cells and some femtocells, which is modeled after the 3GPP dual stripe scenario. And in this slide, you can see the hexagonal layout that is used for macro cell with sectorial sites. We use 3 sectors per site with a co-channel deployment for every sector. And here you see actually a zoom in of one specific macro site together with the femtocell block, which follows the definition in that 3GPP scenario. And every femtocell block is composed by 2 rows of apartment and 2 sets of apartment, and every set of apartment is like 2 apartments on the y-axis and 10 apartments on the x-axis. And femtocells are deployed in these femtocell blocks using a given probability, so to decide whether the one apartment has a femtocell or not, and if it has a one femtocell, whether it is active or not. And some words about testing. Well, we put a lot of effort in testing, and we have tests of several types. We have unit tests that check that specific modules are working properly. For example, test that the RRC protocol is working properly in isolation. We have system tests that check the overall performance of the complete simulation model in some scenarios for which we know reference values of the performance. Well, actually, these are more validation tests where we have performance like a test vector of performance values that comes from, say, a theoretical model of the performance. In this particular case, we can do it for specific scheduler in specific configuration. For example, there has been some paper that tells the steady state performance of the proportional first scheduler in some condition. We have been taking this analytical formulation and deriving some values and then running some simulations to make sure that these values are correct. And then finally, we're using Valgrind to systematically check the code for memory errors. I mean, Valgrind is used in general for the whole ns-3, and we are also running all the tests that we have for the LTE model with Valgrind as well. And finally, a stable version of the code by the LENA project is merged with the official version of ns-3, and thanks to this, it enjoys the build tests which are provided by the ns-3 project. And these build tests basically try to build and to verify the correct build of ns-3 on a variety of platforms, on all the platforms that are supported. And this is, if I remember correctly, it's a most popular Linux distributions are there, like Ubuntu, Fedora with several versions, and also Mac OS is supported, I think, one specific version at least. And well, final words about the ns-3 community. So with the LENA project, CTTC is working in very tight interaction with the ns-3 community. So we merged our first version of the LENA code in the official ns-3 back in May 2012. That was ns-3 release 3.14. And we are currently the maintainer of the LTE module in ns-3. So if you now take the official version of ns-3 and use the LTE module, that's our model, the one we developed for the LENA project. Furthermore, if you find a bug in the LTE model of ns-3 and you file a report on the bug tracker of the ns-3 project, we are in charge of fixing that. And well, we are still working on it. LENA is still an active project. We have new features that we are developing. And well, in particular, the features that you have seen in this presentation today have not been merged yet with the official version of ns-3. We plan to do so for the upcoming version of ns-3, which will be 3.17, and it's due, I think, in April this year. And we'll still be working on newer features in the future. For example, some feature we are working on is UE measurement, so RRC support for it, and also physical layer support for it. Automatic neighbor relation, random selection, which I think I already mentioned before, and handover decision. So far the handover support is only for the execution of handover, but based on in response to a specific trigger. So it means that in the simulation program you have to specify to specifically schedule one handover event. And if you don't, there will be no handover. And after we finally implement this UE measurement from an RRC point of view, and together with the automatic neighbor relation, we will be able also to implement a, say, automatic handover algorithm that makes decision about when to do handover in a, autonomous fashion without intervention of the user of the simulation program. And well, I think that's it. Is there any question?
What is your experience with working in an open source project with a community? It's something hard. You think it's something that really is improving your work, or it's or you do almost everything?
In this particular case, I think we benefit a lot from the community. And the reason is that there is a kind of split between what is the LTE module, which, so anything that is LTE specific, we develop it. But everything that is outside this, we got it basically for free from the community. Like all IP networking support for other protocols, support for a lot of other things, support for the build systems. So yeah, I think overall, the fact that instead of developing a proprietary simulator, or maybe an open source simulator but from scratch, instead of doing this, we went for ns-3. I think it was really beneficial for us. And overall, the interaction, of course, it is not for free, in the sense that at the minimum it will not cost you money, but still you will have to invest a lot of time in properly interacting with the community. So whenever, for example, we have to merge our code with official ns-3 release, it takes a lot of time because of the review process that is necessary for this code to be accepted. And I think that after this review process, our code in the end gets improved. So it's good for the quality of code that we do this. So that's one good aspect. For other aspects, I think we also, for example, got a lot more visibility by joining an existing open source project instead of just writing our own simulator. And I think that nowadays there is a lot of people using the simulator thanks to the fact that ns-3 is already popular. And then when they have to pick LTE, it's a kind of natural choice. If you already know you're going for an open source simulator, I think currently ns-3 is probably the most popular among open source simulator, so it's really beneficial for us in terms of visibility and also of user feedback. So more users are using it, so more bug reports we get, which can help us in fixing the simulator. Of course, sometimes it's hard to keep up with all these bug reports and all these users asking for help. We try to do our best. Of course, we are also on a budget, and this is, for us, it's a funded project, so we give priority to the requirements and the requests of our contractor, and we deal with requests from the community on a best effort basis. But even said that, I think that overall it was beneficial for us.